You ever get that feeling like there are these hidden patterns running the world around us? Well, it turns out you're right. And today, we're going to pull back the curtain on the unseen math that shapes, well, pretty much everything, from your bank account to ancient history. So, to kick things off, let's start with a few questions that, believe it or not, all share the same secret mathematical answer.
All right, first up, let's talk about something we all care about: money. How does your money actually multiply in the bank? I mean, it feels painfully slow sometimes, right? But is there some kind of powerful hidden formula at work?
Okay, now let's shift gears dramatically. Think about this. How can one single, tiny, microscopic virus completely take over an entire population? I mean, what kind of math could possibly describe that kind of explosive spread? And for our final mystery, picture this. An archaeologist digs up an ancient bone. How in the world can they look at it and say with any confidence, yep, this is thousands of years old? So what connects your money, a virus, and an ancient bone? Well, here's the wild part. The answer to all three of those questions is exactly the same. It's not magic, it's just math. A really powerful set of mathematical models that describe growth, decay, and how we make sense of enormous scales. So let's dive in, starting with that first one, growth.
All right, let's kick things off with the most dramatic concept of them all: the incredible and, yeah, sometimes kind of terrifying power of doubling. We're talking about exponential growth.
You know, the core idea here is actually super simple. The more you have of something, the faster you get more of it. That snowball analogy is perfect. When it's just a little thing, it picks up a tiny bit of snow. But once that thing is massive, every single turn packs on a huge new layer. The growth itself is what speeds up the growth. That right there, that's the secret sauce. You know, there's this famous quote that people often say comes from Einstein, and it points us right to where we see this every single day. It's not just about your money earning interest. The real magic happens when your interest starts earning its own interest. And believe me, that changes everything. But here's a crucial detail. How often that growth gets calculated really matters. So, look at this. Let's say you invest 10 grand. If your interest compounds quarterly, 4 times a year, you get a really nice return. But look what happens when it's compounded monthly. It's even better. The real holy grail, though, is compounding it continuously. We're talking every single nanosecond. That's when this mathematical model just goes into overdrive.
And there it is. That financial snowball, well, it more than doubled your initial investment, and you didn't have to lift a finger. That is the raw power of letting growth just build on itself.
Okay, so that's what happens when the engine is going full throttle forward. But what happens when you throw that engine into reverse? Instead of doubling, what if things get cut in half? Again and again and again. Well, that brings us to the science of fading away, exponential decay.
I mean, really, these are just two sides of the same coin. For growth, the big question is how long till it doubles. We call that doubling time. For decay, the question is how long till there's only half of it left. And yep, you guessed it, that's its half-life.
And this whole concept of half-life, this brings us to one of the most brilliant uses for this math ever, radiocarbon dating. See, every living thing, you, me, that tree outside, has a tiny bit of a radioactive thing called carbon-14 inside it. And this stuff has a half-life that is just unbelievably consistent, 5,730 years.
So here's how it works. As long as an organism is alive, it's taking in new carbon, so the amount of carbon-14 stays constant. But the second it dies, bam, the clock starts ticking. The carbon-14 inside starts to decay, and it's not getting replaced anymore. So, by measuring how much is left and comparing that to how much should be there, scientists can literally calculate backward and figure out how long that clock has been running. It's like nature gave us a perfect radioactive stopwatch.
Okay, so exponential models are awesome for things that double or get cut in half. But what happens when the numbers you're dealing with are just astronomical? I mean, so incredibly big that you can't even fit them on a graph. To make sense of those kinds of extremes, we need a totally different kind of tool. We need logarithmic models.
Just think about sound for a second. A jet engine is literally 1 trillion times more powerful than a quiet whisper. How do you even put that on a chart? You can't. Not a normal one, anyway. Logarithmic scales are the solution. They let us handle these huge ranges by focusing on the powers of 10, what scientists call orders of magnitude. So instead of showing the raw numbers, they help us compress that insane range into something we can actually understand.
And earthquakes are the perfect example. Just look at the Richter scale. A magnitude 7.8 quake doesn't sound that much bigger than a 5.1, right? It's only a difference of about 2.5. But, and this is the key, because the scale is logarithmic, every single whole number up is a 10 times increase in shaking power. So the math shows that the big 1906 San Francisco quake wasn't just a little bit stronger, it was over 500 times more intense. That is a mind-blowing difference.
Okay, but let's get real for a second. In the actual world, that perfect exponential snowball can't just keep rolling forever, right? I mean, eventually it's going to run out of snow or, I don't know, hit a tree. Things hit limits. And that's where we need models that are a little more down to earth.
That perfect, beautiful J-curve exponential growth, it kind of assumes you have infinite resources, which we don't. Reality has limits. And that brings us to logistic growth. It starts off looking just like an exponential curve, whoosh, straight up. But then, as it gets close to a limit, what we call the carrying capacity, it starts to level off, creating this cool S-shaped curve. Think back to the virus. It spreads like crazy at first, but its carrying capacity is the total population. Eventually, it starts running out of new people to infect, and the growth has no choice but to slow down.
And hey, this same idea of limits applies to decay too. I love this example. A hot cheesecake fresh out of the oven. It's not going to keep getting colder and colder until it hits absolute zero, right? Of course not. It cools down pretty fast at first, but then it slows until it reaches the temperature of its environment. The fridge. That fridge temperature is its real-world limit, and it's all described perfectly by Newton's law of cooling.
So let's pull it all together. That's the unseen math, right there in front of us. We've got exponential growth, that classic J-curve you see in finance. We have exponential decay, which acts like an atomic clock for history. We have logarithmic scales, which are basically a ruler for measuring giants like earthquakes. And finally, logistic growth, that S-curve that shows us exactly where reality has to draw the line.
I mean, these models give us this incredible power to understand and even predict the world around us. But it really gets you thinking, doesn't it? With all the insane amounts of data we're collecting every single day, what other hidden patterns are we just about to uncover? What will the next great mathematical model reveal to us?